Now that we have an understanding of pointers, it's time for me to introduce dynamic memory allocation. Now with this, we can allocate space dynamically on the heap, which is also referred to as the free store. And essentially what the heap is a section in memory, or in other words, your RAM. There are other sections as well, such as the stack, but the heap is something different from the stack. The heap has to do with dynamic memory, and that is basically a special section in memory for us to go and dynamically allocate memory. But to get started, I want to quickly run through some of these points, and then I want to show you in Visual Studio an example of this so that you have that down. And then again, at the end, I'll show you a few illustrations that maybe if you don't quite get what's going on yet, that hopefully that'll clear it up for you. Alright, we can allocate memory for an object or a variable at runtime. So in other words, we run the program, and then maybe based on user input, we can create an array of 10 integers or 15 integers or whatever the user decides, instead of what we as programmer decides needs to happen at compile time. So we can essentially create an array of a user-defined size at runtime. Now I have to mention that we'll discuss arrays in another video, so maybe in the next video, but that is really where this comes in handy. With the regular variables it may be not that handy, but with data structures such as arrays and so on, it's really useful to create and manage this at runtime. Alright, so how do we allocate memory dynamically? Well, we use the new operator, and with that we can create or allocate an object of a specified type on the heap. It will return the address of the newly created object, and we can then assign that address to a pointer. It's also important to use the delete operator, and that is used to deallocate the memory. We want to basically recycle the memory in the heap. If you use too much of it, eventually your program will crash, so you'll run out of that memory. And you want to make sure to reassign the pointer after using delete, or set it to null pointer, otherwise the pointer is undefined. And this is also referred to as dangling, so a dangling pointer. Quick demo at the bottom here, I have a pointer to an integer, and I do ptr and the assignment operator. Then I use the new keyword, so new int, and that will create a new object of type int on the heap. And now we can use that pointer to go and initialize that integer. The integer does not have a name, right? It's not like a regular variable. That's why I discussed objects and variables in a bit more detail in some of the previous videos, because this object doesn't have a name like a variable. This is not x or y or something like that. It's just an object in the heap, and we access that only using this pointer. And then to clear up that memory so we can recycle that memory, we use the delete keyword followed by the name of the pointer. Now of course this won't delete the pointer variable. This will simply deallocate the memory that it points to at the address stored in that pointer. So of course once you have the object created in memory now, and you have that address assigned to the pointer, then we use that pointer to access the newly created object. So we can dereference it to assign a value to it, or to change the value, or to print it out, or whatever you want to do. You can also have two pointers pointing at the same object, and in that case let's you do delete on either one of those pointers, then both of those will now be dangling, and you must make sure to define those pointers once again, or however many pointers you have pointing to that object. If you deallocate the pointer using the delete keyword, then all pointers pointing to that object will be undefined or dangling, so then you have to go and set them to null pointer or set them to point to something else. So here is a quick example. I have a pointer to an integer, I'll just call that ptr, or pointer for short. Then I do pointer and the assignment operator, the new keyword, and then integer. So this will create a new integer object in a memory section called the heap or the free store, right? And if this is successful, it's going to return the address of that and store it in this pointer. The thing is, you can eventually run out of memory, right? And notice here I'm not referencing that pointer or anything like that. I'm simply using the name, so ptr, and then I do the assignment of whatever address this operation returns. And how do I remember that? Well, this is going to create a new object in memory. And how do we get to that? Well, we need the address of the object to actually get to it, right? And of course we store an address in a pointer. So again, maybe you can remember it in that way. Previously, if we had an integer x, for example, we would have to do the address of operator and then do x, and then we assign that to the pointer. Then we can go and dereference that. So similarly in this case, we now have this object in memory once again, and we want to assign values to it. Basically we want to read from or write to that object. Well, we can do the dereferencing as we are familiar with already, and then we can do assignment, or here in the console output, you can see I also do the dereferencing, and in that way I can now fetch what value is stored at that memory location. In this case it will be 15, so I print it out, and then to free up that memory again I do delete ptr. Now what will it delete? This 15? No, it's actually going to delete the object in memory. Okay, where is the object in memory? Well, this pointer now stores the address of that object in memory that we are going to delete, or deallocate basically. Now this is a really small program, so we should not run out of memory, but it's a good habit to get into to go and delete whatever memory it is that you allocate. Alright, so delete that, and once we've deleted it, then we'll have what is known as a dangling pointer. So you want to make sure to set that to either null or set it to point to something else. Right, I'll build and run that, and you'll see we get 15 printed out. In this next section, I want to provide a really high-level introduction to the memory segments that are used by our programs. So firstly, what do I mean by a segment? Well, the term segment comes from memory segmentation, which is a memory management technique. You also have paging. Now, I'm not going to go into too much detail on those memory management techniques. You can read up on them if you really want to. So I have these different segments. You have the code, also known as the text segment, the static segment, and then also the stack and the heap. So we'll start at the bottom here with the code or the text segment. The code or the text segment is some object code that is the output of the compiler, or it will include some executable instructions. So basically it's our compiled program, right, that is in this code or text segment, and it's typically read-only. Then we have the static segment, and this is going to store your global and static variables. Then we have the stack. Now this stores function parameters, local variables, so whatever variables are local to that function that is currently on the stack, and it's going to keep track of currently active functions. Now some of the upcoming slides will illustrate the stack to you and how we stack functions and variables. Next we have the heap, where dynamically allocated variables or objects live. We are primarily concerned with the stack and the heap for this lecture and for this lesson. So in the next few sections I'll talk about the stack and the heap in a bit more detail, starting with the stack. So you are familiar with the idea of a stack, right? So a stack of books, or a stack of poker chips, or coins, or something like that. But the stack data structure is restricted in the sense that we can only access from the top. So let's say you have a pile of books. You're only allowed to sort of access the top book. So let's say you want to add a new book. You can only add a new book on top of the stack. You cannot like lift the stack of books up and place one at the bottom, right? Or in the middle, for example. You can only like place one at the top or remove from the top as well. A summary for you here. A stack is a data structure in which the addition, deletion, and retrieval of elements are restricted to occur at the top end of the stack. So basically at a particular end or one end of the stack, and that end of the stack is referred to as the top end of the stack. Computers use stacks to implement function calls, especially useful for recursion, which is basically a term used for functions that call themselves. I will talk about recursion a bit later on in the course. You have a few operations that you can perform on a stack. So as I mentioned, addition, deletion, and maybe you also want to retrieve elements, so to see or to inspect what that top element is. It may be a variable, for example, or an object or instance of some class or a struct. Some of the operations, you have the push operation. Here we insert an element at the top of the stack, and then you also have the pop operation, which is going to delete or remove an element from the top of the stack. Now if we insert elements into a stack and then remove them, they will be in the reverse order. So let's say three integers, 1, 2, and 3. We push those integers onto the stack. Then once we go and pop those off, so maybe we inspect the first one, pop it off, inspect the next one, pop it off, and then inspect the final one, right? Then we'll get the order 3, 2, 1. So it's going to be in a reverse order. And this attribute of the stack data type is referred to as last in, first out. And you can see it in the example. So the last element in was an integer with the value 3. But then when we start to retrieve those elements, you'll see 3 is first, then we pop that off. We retrieve or inspect the next element, we get 2, and so on. So last in, first out. So I would like to mention that the stack is a data structure similar to the array that we've discussed already. And of course we have other data structures as well, such as again the stack, linked lists as well, binary trees, which are quite complex as well, and you'll study that maybe in another module on data structures. This module won't really go into data structures all that much, which is why I'm just explaining the basics to you right here. But the stack is actually something that you can use in C++, just like you can use an array, and queues is actually another one that I'm missing here. So you have stacks and queues and the other ones that I mentioned as well. And for this illustration, I'm just adding objects onto this stack instead of something specific, because it can be, a bunch of different things. Again, it can be a variable, it can be an object or instance of a class, or maybe a struct or something like that. So we're just going with an object here. To start off with, let's say this is some program, and we already have object 1 and object 2 on the stack. Then I go and push object 3 onto the stack. And then later on in the program, maybe I decide to remove those objects. So here I can't just remove whatever I want, right? This is basically a restricted data structure. So I have to do pop, and that is going to pop or remove the top element or object from the stack. Then I do pop again to remove the next one, and so on. It's important to remember that the stack is accessed only from the top, whether you want to push elements onto it, pop elements off of the stack, or if you want to return the current element at the top of the stack. In other words, if you want to access that top element, so maybe to print it out or something like that, okay, you cannot access from the bottom or from the middle of the stack. Maybe you can write some function called top, and that will return the top element. And so to iterate through the entire stack, you'll have to go and return the top element, pop that element or object off of the stack, then return the next element, again maybe using a function called top for example, and so on, if you want to again go through the entire stack. So go and repeat that process until the stack is empty, of course, in which case you'll exit the loop. Alright, in this example I have two functions, print double and print int, which will just print out whatever argument we pass in. And I start with the main function on the stack, and once we step into that first statement where we have the print int function, a couple of things will happen. Firstly, we need some return address so that program execution can resume in the calling function. And we can think of these green boxes in the stack in this illustration as something called an activation record or a stack frame. And when we call a function, we create one of these activation records and we push it onto the stack. And of course, once the function terminates, we'll pop that activation record off of the stack and return to the calling function. Local variables, that includes function parameters, will also be allocated on that stack. And for demonstration purposes, I'll add them in that green block as well. So at this point, we've pushed a few things onto the stack. Now it's time to transfer control to that function. So in other words, program execution will move to that function. And I would recommend that you study some assembly language, just the basics maybe, to get a better understanding of how some of these things work on a lower level, because that is a very manual approach. Because here we don't see it, we don't actually have to do the jump to some function command, for example. We just write the function and a lot of that stuff is done for us. Basically there is some overhead in calling a function that we don't see here. Now again, this is not an assembly language programming course, so I'm not going to show you all of those details. I'm just going to show you a very high level sort of example. So basically at this point we have the activation record on the stack. So we jump now to the print int function. In the print int function, I'll just go and print that integer out. Execution will move to that closing curly bracket. And basically from here we'll do jump again, so we'll transfer a control back to where that return address was that we pushed onto the stack, so that we know where to go back to basically. So we go back to the main function, and then we just pop that function, and whatever local variables or parameters we had for that function we pop from the stack. And the same thing is going to happen with the print double. So once we step into that line or that statement, we'll push another activation record onto the stack. In this case for print double, including the return address and everything else, we'll jump to that function, execute whatever is in its body. So in this case we simply do a print again, so console output. So once we are done executing all of the statements in the body, execution will reach the closing curly bracket. We are basically done with that function now, so we will jump back to the main function to resume program execution in the caller, which again was main, and we'll just pop that function off of the stack again. And of course we'll continue executing the other statements in main. Okay, so this example is a bit different. In the main, I simply call printInt, and then I'm going to call printDouble in the printInt function. Again, I have the main function on the stack. Once I step into the statement where I have the printInt function call, again we'll push an activation record for that onto the stack, and we'll push the return address and so on. We'll create space for the variables and so on as I explained, and then we'll jump to or transfer control to that function. Okay, so in printInt, I simply go and print out I. So I do console output and I again, but you see on the next statement I have printDouble. So when I step into that statement, I'm going to create another activation record for that function onto the stack. Again, I'll push the return address, and now what we do is we transfer control to that printDouble function. So we jump to that, and here you can see the printInt function call is still on the stack. Alright, so I do the console output. Eventually execution will reach the closing curly bracket. Then we'll jump to or transfer control back to the caller. In this case, the caller is not main. The caller in this case is printInt. So we jump back to printInt, and then we pop printDouble from the stack. In this case, we don't have anything more to do in the body of the printInt function. So execution will eventually reach again the closing curly bracket, and then we'll transfer control back to the main function, so to the caller again, and then we'll pop printInt from the stack. Now again, the goal with these examples is just to provide a high-level overview of what's going on. So don't worry too much about what's going on behind the scenes, so on a lower level, or like exactly the order in which things are done. And typically why you'd learn assembly language in the first place is to go and optimize your code, but you'll pretty much have to be an expert if you want to do that these days, because again, today's compilers are really great at optimizing your code. But again, just to get a basic understanding of what's going on a lower level, maybe just take a basic course on assembly programming somewhere. Okay, let's look at this example in Visual Studio. Now I've made a few changes to this. In printInt I have the start of printInt, and over here I have end of printInt, and a similar thing in printDouble. I have start of printDouble, end of printDouble, so I'll print those out to the console when we evaluate those expressions. Alright. I'll set a breakpoint right here because that's where I want the program to pause, and then I want to step through it line by line. I'll run the local Windows debugger, go and step into that line, and then of course we'll jump to over here and step into that. When I step into this line now, we'll print start of printInt out to the console. I'll just bring up this here and you'll see that is what we get. And I'll continue on, step into that. It'll print out I once you step into that line, and as soon as we reach this line, if I step into that line, then of course we'll jump over to the printDouble function and we can step through those. Here we reach the end of this function, and as soon as I step into this, we'll go back to the caller, which is printInt, so I'll step into that. You can see execution is now over here. I'll step into that line, and then we'll print this out, end of printInt. But the point is here we don't go back to main, right? PrintInt was still on the stack, so you go back to printInt, finish whatever statements you had left, and right here we are now at the end of this function body, so we'll go back to main until we finish these final few statements and our program will exit. In the console again you can see we do start of printInt, we print out 5, we do start of printDouble, we print out that double, then we do end of printDouble, and then we go back to the printInt function where we print this out, end of printInt. Alright. Now this is great for debugging, but it's useful to look at the stack or the call stack to try and keep track of things. So it's really useful if you can draw that out, or you actually have down here, you should have it, the call stack, or you can go to debug, Windows, and you have the call stack right here. So if I restart this program, step into that, you can see the stack. I'll just go and step into that line, step into those lines, and step into printDouble. And you will see on the stack we now have main, we have printInt, so main is down here. Down here we have external code and all that stuff. We don't care about that. We have main, then we have printInt, and then we have the double, printDouble. I'll step into these lines until we get to the final closing curly bracket. We go back to the previous function, to the parent function, which was printInt, and you'll see printDouble will get popped off from the stack, because we are now back in print int right here in the call stack, and so on, and eventually we'll go back to main, and then print int will now also get popped off of the call stack. So this is useful, but as I mentioned, sometimes it's really useful to draw those out as well in maybe your study notebook, especially when you have reference parameters to try and keep track of how values change. And as I mentioned later on in the module, in another lesson, we'll talk about recursion, where these tools will be very important because recursion can be a bit confusing, and whether you use the debugging tools in Visual Studio or whether you go and draw things out manually. So maybe in your study notebook, and it's really useful to think of these as, again, you are adding functions onto a stack, right? It's not just, okay, I'm calling this function now, what happens? Well, you're adding it onto the stack, including whatever variables it has, and so on. When you are done, that gets removed and you move back, right? You move to the item that is now at the top of the stack. Again, that's very handy for debugging if you understand that concept. Now we've talked about the stack. Next I want to talk about the sort of relationship between the stack and the heap and what happens when we create or allocate a dynamic variable on the heap. And these examples should give you a better idea of what I mean by memory leak, where I have an object in the heap that is inaccessible. Okay, so if you have a difficult time understanding that concept, some of these illustrations will help to clear that up a bit. In this demonstration on dynamic memory allocation, I have the program to the left, and then I also have the stack and the heap. So your C++ program starts at the main function, that is the entry point for your program, so that basically gets pushed onto the stack. So the sort of green container that we have here, that is the main function, and then of course we also have variables in there, so the pointer variable goes on the stack as well. Of course, in the main function we have the pointer to an integer. Then I go and create a new object in the heap, an integer, so that will allocate enough space for an integer in the heap, and if that is successful, it will return the address of that and store it in the pointer. Then I just deallocate that, and then I store the value 15 in that object. Then of course I do the console output, which will print out 15 to the console. Now in the statement where I use the delete operator, that is going to deallocate the memory in the heap wherever that pointer is pointing at. Now it's important to realize that once we go and deallocate that memory in the heap, that this pointer is now undefined. That is why I deleted the whole thing and why I did not leave like the memory address or something like that. Because in some instances, if you go and experiment, you'll actually notice that the pointer does not even keep the address where it was pointing. Sometimes even the address that it stores changes after the statement, which is a bit weird, but that is what happens. It is undefined, meaning that you should not try and use it at all until you go and redefine that. So after that delete operation, you now have an undefined or dangling pointer, and you want to set that to null, or you want to set that to point to something else. So in other words, again, you want to redefine that pointer. And of course, the reason for us deallocating that memory in the first place is so that we can essentially recycle that memory, or so that our system can now reuse that memory for something else, maybe another variable that you create later on, another dynamic variable. Alright, so I'll rewind just a bit. And in this example, I actually have added another pointer. So pointer 2, also a pointer to an integer. And I set pointer 2 to point to wherever pointer 1 is pointing at, which of course is this dynamic memory on the heap, or this object in the heap. So I dereference that initial pointer. To print it out, we should get 15 again printed out to the console. The point of this illustration is that after the delete operation, both of those pointers will now be undefined, also referred to as dangling, because that object is deleted or removed from the heap memory basically. So you free up that memory and you now have these two dangling pointers. But later on I try and use pointer 2, which then of course I'll get an error. Now as a quick reminder, of course you should also not dereference a null pointer, because that's not really a valid address. So in some cases you can either check for null, whether it's a null pointer or not, before you use it. That's also a good idea. But in the case where it's dangling, your program will just crash. So again, the point with this is make sure to define your pointers after the deallocation operation. Okay, the goal with the next example is to go over the concept of a memory leak again and how that happens. Maybe this will help you visualize what's going on if you don't really get what's going on from just looking at the code, right? Okay, so I have a program again to the left. in main, all I do is I call the function leak memory. So as soon as we step into that statement, we'll push a stack frame for the leak memory function onto the stack, and that will include memory for the local variables. So we have local ptr, which is a pointer to an integer. Then when we step into the statement in the body of the leak memory function, we'll create that object in the heap. So we'll allocate memory for an integer in the heap. And if that is successful, so if there's actually memory left to go and allocate that object, then we'll assign the address of that object in the heap memory to the local pointer. And of course we can now go and initialize it and use it using that local pointer. But in this case, I'm just going to move execution to the closing curly bracket, in which case we are done with that function. Program execution will now jump to the main function. Then we'll pop the leak memory function from the stack. You can see where the problem comes in here. If we go and pop that stack frame off of the stack, it will delete the pointer as well. But of course it's not going to delete or deallocate the memory that's in the heap, the object that's in the heap. So you still have that dynamic variable in the heap somewhere, but we cannot access it because the address was stored in that local pointer in the leak memory function, and we did not return that address. We don't have access to that address anymore. We don't have any way to access that object in the heap memory now. That means we have a memory leak. And of course, if you do this over and over and over again, eventually you'll run out of that heap memory. Of course, this is just an integer variable, but you can have huge objects. One struct instance can have many variables or members right within a single instance, as I talked about before. Also, again, this is a small program. You have huge programs with tens of thousands of lines of code, or hundreds of thousands, and even huge programs like Unreal Engine has millions of lines of code. So of course, if you keep making these sorts of mistakes, eventually you'll run out of that heap memory and your program will crash, or it will throw you some error depending on whether you try and catch that error or not. Now we'll probably talk about how to catch errors in a later lesson. We're not going to talk about that in this lesson. So I hope this gives you a better idea of what's going on, why it is actually a memory leak, and why you should use the delete operator to deallocate whatever memory you have allocated on the heap. And of course, in this example, you want to do that in the leak memory function in a final statement. So before that function will terminate and get popped off of the stack, right? You want to deallocate the memory pointer to by a local pointer, and in that way you won't have that memory leak. So back in Visual Studio, I have the leak memory function here. So what you want to do to fix this memory leak is you want to do two things, not just delete. Even though we are not going to use local pointer again, just get into the habit of setting that to null pointer, or in other words redefining that pointer. This will make sure that we can call this function over and over again, and it will create this memory. Then we can go and destroy it later on, or in other words deallocate it or free it up again so we can use it for something else. Okay, so I hope you found this useful and interesting, and I'll see you in the next lecture.